All right, we have a few problems to go over.
Oh, let me check that.
1, 2, 3. Oh, we gotta bring it up on the screen.
Sarah.
I thought it was hard.
Three equations, 3 variables.
No, I didn't want
I used to.
So you didn't want to work.
to.
Yeah, they got us.
Number of
I did it too.
Number 1. That's why we have trouble. Anyway, like I said, some of you are not noticing that these are the same problems we did in PCH last year.
Oh, we did. Yeah.
Yeah, but if you don't remember, well, it's not going to help, right? Okay, number 1. How many 4-digit whole numbers are not divisible by 11? Well, just write them all out in a circle as you go.
I did it and I couldn't count.
So that's why we're going to do that. Okay, so what we're going to do is we're going to count how many 4-digit whole numbers are divisible by 11 and then subtract it from the total. Okay, can we get the total at least?
Yes.
How many 4-digit whole numbers are there? Well, you can go like this. What's the smallest 4-digit number?
9,000.
1,000. What's the biggest 4-digit number? 9999. How many numbers is that?
9,000.
Yeah, you just subtract and add 1, right? Okay, if you read, okay, let's say you read a book. It's probably not a math book, right? And you read pages 2 through 6. How many pages did you read? 4.
4.
No, you read 5. You subtract and add 1. Look, 2, 3, 4, 5, 6.
Finger bad.
No. You subtract and you add 1. So you subtract and add 1, 9,000. Or how about using multiplication principle? How many choices, if I'm making a 4-digit number, how many choices do I have? 9. 0 cannot be the first digit. How many choices do I have for the second digit? 10. 10. Multiply 9,000. Okay, so now the hardest part. Out of those 9,000, how many of those are divisible by 11? Well, what's the smallest 4-digit number that's divisible by 11? Wait, let me call on somebody because I'm sure you did the work, right? Tran. Every time I look at this side of the room, I see Tran, and this side it's Wong. Tran.
1001.
Very good. How did you know that?
Because
No. Tell me. No, don't listen to anybody.
1,100 minus 99.
Okay, that's very good.
Wait, what?
Say that again, Tran.
1,100 minus 99.
Because both of these are divisible by 11. That's divisible by 11, right?
How do you get that?
11 times 100. 11 times
I
100.
thought you just do 1,000 and adjust.
Just keep guessing.
But 1,000 is not divisible by 11.
Yeah, but
So you
Yeah,
adjust.
but
You adjust.
So you adjust.
Okay, so but this is the same trend. Were you in my class last year? We went over the divisibility test by 11.
We did?
Wait, I forgot.
Okay, Pui, I'm calling on you next. Okay, let's suppose we have a really big number. 235,786, 430, give me a number. 8. Is this number divisible by 11?
Do it all.
Oh, it's the 2 digit.
Yes. Okay, you start with the first digit, then add up every other one like that.
Seriously?
I showed you this last year.
Wait, I did not do that.
Okay, well, somewhere in elementary school you should have learned. Okay,
It's
what is 2
remedial
plus
math.
5 plus 8 plus 4 plus 8? Quick. 2 plus 7, 15 plus 27. And then starting from the second digit, you go every other one like that, and you add those. 3 plus 7 plus 4. 3 plus 7 plus 6 plus 3. 10 plus 9 is 19. Subtract. That's 8. Is this number divisible by 11?
No.
No, so that number is not divisible by 11.
How does that
One.
That's the test!
One.
How does 1001?
1 minus
Okay, well,
0. Oh.
Just do it out. Like Fran said, just go, okay.
Wait, why is
I'm going to divide 11 into it and see if you get any remainder then. How's that?
Just do modulo.
Look, we're taking that out just to figure that out.
Synthetic division.
No, there's no synthetic division, there's no variables.
I gotta make a series.
Okay, so what's the next multiple of 11? 1, 0,
12.
1, 2. 1, 0, 2, 3. And you keep going until you hit the last multiple of 11. 9, 9, 9, 9. How do you know that's divisible by 11?
0,
Zero.
0.
Look, well, yeah, look. 18 minus 18 is 0.
Why is 0 divisible by 1?
Huh?
Why is
Because when
zero?
you divide it by 11, it has 0 remainder.
Oh.
Anytime you have 0 remainder, that means it's divisible by that number.
That's why
Alrighty then, hey, this is an arithmetic sequence. That's what we're studying. What's the formula for arithmetic sequence? A sub n equal a sub 1 plus n minus 1d, right? So what we want to do is we want to find how many terms there are in this sequence, right?
Yep.
So that means solve for n. Okay, what do I plug in for a sub n? 9999. That's the nth term, except we just don't know what n is. What do I plug in for a sub 1? What do I plug in? What do I plug in for d? 11, because that's the number you keep adding by. So if you take this equation and solve for n, that's how many multiples of 11 there are here. Okay, and then subtract that from the total. So the answer is going to be 9,000 minus whatever this number is. I'll let you compute that number. You guys can do it, right? Can you repeat this problem on the test?
No.
Yeah, you're right. The one on the test can be much harder.
Why?
Because the practice
The
test.
plus the
She's saying
reciprocal
no.
series, remember that?
The
The
reciprocal?
AMC.
No, don't give him ideas.
No, is it arithmetic or geometric?
Please no.
It's infinite.
No, that would be next chapter. That's next chapter. That's series. This is sequence. Next chapter, maybe. Okay, number 2. Number 2! That's exact. I put this on the quiz. Did you like dig out your PCH quiz from last year?
Yeah.
No. Yes.
Hey, this is the problem. Okay, here is a 4-term sequence.
Wait, why is that?
The first term is 2. Really, for real? You guys like this? I don't know what you're doing, Mr. Farr. I've never seen this problem in my life. The first 3 are geometric. Okay, if the
Oh, I
first term
remember
is
this.
2 and it's a geometric series, how do I label the second term?
2r.
2r, because you multiply it by some number that I don't know. Right?
2r squared.
Then you multiply it by that same number again, you get 2r squared. Okay, now, the last 3 are arithmetic. So these 3 are arithmetic, which means they have a common difference. So what equation can I write?
2r squared.
This minus this gotta equal that minus that. How come?
Different.
Is that a dot?
Yeah.
Okay, look, we erased it. Okay, look at it right here. Arithmetic, it is here. Arithmetic sequence. What is this minus this?
11.
What's that minus that?
11.
What's that minus that?
11.
Yeah, that's why. This minus this equals that minus that. Hey, it's a quadratic equation, monsieur.
Dude.
I'm going to make one side. How do you say 0 in French? Oof. Oof, right?
Yeah.
Yeah.
I think
I think that's correct.
Wow.
No,
Yes.
isn't it?
It's
What is
zero.
oof? Egg. Yeah, egg is a 0, right? Doesn't egg mean 0?
French.
No, I thought, no, when I took French in 11th grade, I'm pretty sure
Wait, one
my
side
teacher said
oof.
oof is like the slang for 0. Because you get a goose egg, which is like a 0. Okay, whatever. Divide by 2. Hey, gonna have 2 answers. See, remember I told you guys last year in PCH?
Yes, and
No, because some people go guess and check. They go guess and check one, but they're not gonna guess and check the other, because it's a fraction. I put that in to thwart the guess and check people. Tran.
4 numbers.
5 and 3, 3 and 5, minus plus. So r equals negative 5 halves, or 3. So that's why you get 2 answers. See, the people who guess and check, Tran, I remember you on the quiz last year. You went 2, 6, you multiply by 3, 18, and then you get 30, and then look, you add 12, it works.
Yeah.
I got the problem correct.
Oh, yeah.
Oh, then what about this answer? That's why you had, if this problem was 6 points, you had -5.
Because you know it's.
Try to dig out your quiz. Go look.
I left it at home.
Algebra, there's 2 roots.
You
I
actually
bet you can't even find
I
it.
think so, yeah.
What?
Okay, number 3.
Tree.
Write it. Boo! Okay, you're gonna really enjoy the one I gave you on this one. 1, 5. Okay, to get the third term, no. Yeah, to get the third term, you multiply the previous one by 2, subtract the one before that, and then add 3. Okay, let me see if I can do it. 10 minus 1, 9 plus 3 is 12. Did I do that correctly? I'm sniffing pentagonal numbers.
Oh,
Anybody sniffing pentagonal numbers? Olga? Math team people automatically just going pentagonal. Okay, let's pretend we don't know pentagonal numbers. I want to get one more term. Shh.
Smell.
24 minus 5, 19 plus 3 is 22. Yup, pentagonal numbers. What pentagonal
Is this
numbers?
the dots?
Yeah, I know.
Dots.
I'm going to do one more for funsies. 44 minus 12, 32 plus 35. Okay, so what's the pattern here? Now, you have to write the explicit formula, not a recursive formula. Well, they gave you the recursive formula anyway. So can I just break this down like the one on the quiz was n times n plus 1?
Yes.
No, this one's not as, okay, what is it?
Oh, I thought you meant the one with the plus and the 2 levels or something.
Yeah, so, okay. No, but before you get to the levels thing, don't you want to see if you can break the code first? Or you want to just go to the app?
What app?
So
Let's break the code.
The app, which, like,
Oh.
this is the app. I just made
Oh,
that one
yeah.
up. You look at the differences.
What app?
The method of finite differences app. 3. And then 3, 3, 3, 3. Hey,
Check.
the formula is gonna be quadratic. Just like the quiz one. To break it down is like, okay, I don't wanna use the app, I wanna use my mathematical prowess. Like, okay, when I see 1 and then, okay, this is what I think. 1 is like 1 times 2 over 2. That's what I'm thinking.
Just know what you think.
5
What do you think?
is 2 times 5 over 2. No, you look at the numbers, you don't see anything, then you know what you should try, like, what about double that number? Or 3 times that number or something? What about 12?
3 times.
Look at the pattern. 3 times 8 over 3.
What?
I'm breaking the code without the app.
I can't do that.
Wait,
It's over 2. Wait.
I know, over 2, over 2.
Oh, that's not right.
Over 2.
Over 2.
It's over 2.
Oh yeah, over 2. What am I gonna say? 4. 4 times 11 over 2. 5 times 14 over 2.
I broke it.
Yeah, you broke the code. So, how do you generate the numbers 1, 2, 3? N. How do you generate the numbers 2, 5, 8? 3n minus 1. And then how do you generate 2? 2. There you go, there's your formula. That's called breaking it down.
Come on.
I mean,
Or would you rather just use the app? Why are we saying that? That's like,
It's like boring.
it's called using the method of finite. I don't care how you do it, you just gotta do it. Is this ringing a bell at all?
Yeah.
I blame Algebra 2. No, Algebra 2, they used to cover this in Algebra 2, but then the last 10 years they said they didn't have time. Number 4.
J.
There's
40,
one.
number 40.
Oh, 4 O and J.
Orange.
Okay, so let's do J.
Yeah.
Boo!
Oh wait, I remember this.
Negative 1 to the n plus 1 all over n.
Yeah.
Okay, if you don't know what's happening, write out the first few terms. Just plug in 1, 2, 3, 4 and see what you get. 1, negative half, 1/3, negative 1/4. Do I need to go more? I will. 1/5, negative 1/6, It's oscillating back and forth, positive, negative, but the numbers are getting closer to 0. The limit is 0. Okay, let's see if you guys are, okay, we're gonna start this chapter, chapter 10. Now, what would happen if I add these numbers up? Who's gonna impress me here?
Oh, telescope.
Well, no. Yeah, but no. If I add these numbers together, you will get. Olga?
Is it still one that's?
Oh wait, the 1 plus 1 half.
Yeah, it is. Add these numbers up. And what do you get?
1 half, 1 plus 1 half plus 1 third.
No, no. 1 plus negative half.
Is that pi over 6? Or is that another?
No, no, no.
Power 2.
Power 3.
Pi.
Natural log 2, for Pete's sake.
Always not.
2.693.
No, for real. Today's lesson is the power series, and this is one of them. This is like today's lesson right there. Here, let me show you what we did last year. Plot the partial sums. What's that? Okay, 1.
1.
Plot 1. Okay.
Oh, and then it goes back
Subtract
and
the half.
1 half.
Yeah. Add a third.
No.
Subtract the 4.
Keep
Add
going,
a
right?
fifth.
3, 4.
Subtract the 6.
Keep going.
Add 1 7.
Natural log 2.
Subtract. So you can see that it's getting closer and closer to some number that's there. That looks like 0.693. Natural log 2.
Looks like 3, 4.
Okay, we're moving on. Oh. Ooh! Okay,
There we go.
last year at PCH, I told you that problem is on the test. I'll tell you right now, this problem is on your test. Something like it. Something like it.
17.
N plus 1. And I remember last year, you guys did very well on this, unless you didn't. N plus 1 factorial. Mr. Park, I'm noticing like something here. Yeah, the reason why I gave you this is because at the end of chapter 10, there's a test you have to do. You don't know what the test is, but you're gonna do the test, and you're gonna get this, and you have to find the limit of it. It's called the ratio test. Does that sound familiar? Okay, anyway. How do I find the limit of this, monsieur? You simplify it. Okay, just look at that. N factorial all over n plus 1 factorial.
N.
Hey, you can simplify that. Maybe you can't. Isn't that just 1 over n plus 1?
Yes.
Can do or no can do? Remember when we did combinatorics last year, I said you gotta be able to work with factorials? I thought you were kidding, mister.
What's comfort?
Look, okay, look, let's pretend we don't know anything. What is n factorial? N times n minus 1 times n minus 2, all the way until you hit 1, right?
Yeah.
What is n plus, that's why I said monsieur. What is n plus 1 factorial? N plus 1 times n minus 1 times n minus 2, all the way until you hit 1. What's left? 1 over n plus 1. Okay, can we get that far? Oh, hey! That's like to the first power. What do you do when you have the same base, you subtract the exponent? So isn't this the same thing as n plus 1 to the n over n to the n?
Yep.
Subtracting the exponents.
The end comes out.
Hey, you
And
should
then
probably-
since both of them are to the nth power, you can just do this.
Oh, you are yours.
And then, hey,
You
you somebody, lift and separate 1 plus 1 over n to the n. What's the limit of that? E to the 1. Remember? 1 plus box over n to the n. If you take the limit as n approaches infinity, it's e to the box.
It's always here.
E to the 1.
25 actually.
No, not memorize.
That's my quiz, man.
I could have been an engineer, but to endure pain every day.
Took us through that.
Yes, engineers, you probably have to endure pain every day too, but you get paid more. Okay, I'm telling you, this problem, I made the test this morning, this problem's on there. You're gonna have to work with factorials.
What's in the box? Is it gonna be like 2 boxes? Yeah.
Yeah. Something's gonna be a little different. Okay, and then finally 6D. Wait, are you sure we don't have to discuss anything else on that number 4? Because I know some of you are behind somehow. Are you sure?
Which one should we discuss?
I don't know, I'm looking at it all, like you can,
6D.
6 what?
There's a 6D.
No, I'm talking about number 4.
I've done like-
So everybody can do all of number 4. Okay, I'm gonna call on somebody, I'm gonna shout out a problem. Let me pick somebody at random.
Wrong.
I see people looking down, that's the people I'm gonna call on. Angelo,
What?
4n.
Negative infinity.
Oh, I saw you look at the bottom. Very good. Very, no, the bottom of your paper.
Okay.
That's very good. You know why it's negative infinity?
Yeah, kind.
A
Because it goes
bit.
like this.
Wait, which one?
The ends.
Natural log 1 over n. What is the limit of the secants? Why is it negative infinity? Well, there's two ways. There's 2 ways you can think about it. What happens as n approaches infinity? Doesn't this go to 0? And then what is natural log? Now this number is not 0. It's getting closer to 0. What is natural log of a very, very tiny number?
Negative
Natural log of
infinity.
0.00000011. Yeah, because the graph looks like this, right?
Woo!
So when x is like very tiny, the y coordinate is just a huge negative number, yeah? So negative infinity would be the limit. Or would you rather think of it this way? I'm going to use my properties of logarithms. Isn't that the natural log of n to the negative 1?
No.
I'm going to cough up the hairball in the front. Why do I say that? And then as n approaches infinity, what does that go to?
Infinity.
Infinity and then negative, so negative infinity. So there's lots of ways you can think about it. I mean, use graphs, use whatever you have to. Use all the tools in your tool belt. I only have a small hammer. And maybe a screwdriver.
Just have a pencil.
Okay, and then finally 6D. Aha! Okay, I'm going to tell you right now, by doing this problem, it's going to help you on the fix. This problem. 0 to infinity, x e to the negative x dx. Oh, and just by the way, make sure you're going to get this problem, but then you have to rotate things around like the x-axis and y-axis. Disc shells and washers. We had it on the whole word. And then I wouldn't be surprised, okay, I'm just going to give you a hint here, what the heck. I wouldn't be surprised if you have to use partial fractions and trig substitution.
That's
Or
so
integration
rare.
by parts even.
What about tabular?
Oh, this is right here? This is tabular? Okay, what makes this integral improper? The infinity. So replace that with a letter and take the limit as b approaches infinity, right? Now, what does this graph look like? Let's just graph it for funsies. Plug in x equals 0 and then it looks something like this. Right? So what we are doing is we're finding this area here. Now, is that a finite area or does it converge to infinity? Well, that's why we're doing this problem. So how do you find, so this is what we want to compute. Compute that. Tabular. X, 1, 0. E to the negative x, negative e to the negative x, e to the negative x, tic, tac, toe. Hey, who was the person that did it like Jaime Escalante? There was one person in this class.
Probably small.
Or maybe it was AB. Because you know how Jaime Escalante did it like this. Tic, tac, toe.
Wait, why does it do it like that?
I don't know. No worries, mate. Okay, that's the antiderivative, correct?
Yep.
From 0 to b. Oh, I know what happened last year. I remember now. It's all coming back to me in DC. Nobody asked this question the day before the test. And there was something on the test. And then I think only like 3 people got the problem. Lee, Kong, and Cho.
Jason Cho.
Nathan Lee? Yeah.
Whoa.
I had Lee, Kong, and Cho.
Yeah, I was there.
I would remember. Okay, plug in the top number. Negative b e to the negative b. You guys are so lucky we're going over this. You guys are so lucky. Plug in the bottom number. 0 minus 1. Okay, so what do we got? Negative b. You know what? I'm not going to even distribute the minus sign. We'll just leave it like this. Now, let's take the limit as b approaches infinity. See how, notice I don't write, notice how I don't write equal signs, because on the AP exam, if you put an equal sign and they're not equal, you get points taken off right there.
Oh no.
See, like this, is equal to that, but it's not equal to this one. You know what I'm talking? Because there's no limit in front of it. Okay, now, if I take the limit as b approaches infinity, what happens with this one?
Zero.
Okay, let's do the easy. Let's do the easy one first. What is this one?
Zero.
That goes to 0, because that's like 1 over e to the b, right? What about this one?
Indeterminate. Negative 60 times
1.
0.
It's 0! Therefore, what is 0 minus 0 minus negative 1?
1.
1. This area is exactly 1 square unit.
Wait,
What? Okay, this one I get this the part because that's 1 over e to the b. Everybody see that goes to 0? Well, isn't this the same thing as negative b over e to the b?
Yeah.
Now what happens when both the top and the bottom both go to infinity? N to the n Feppel. Polynomial, exponential. Which one goes to infinity faster? Exponential.
Feppel. 0.
Yeah, well, that's kind of late for that now, so that goes to 0.
Oh.
If the bottom grows faster than the top, it's 0. Why, did you guys even think about that?
Yeah.
Because I forget what they did last year. Like, everybody got this one, and then something happened over here. Only Lee, Kong, and Cho got it.
1. Infinity. 0.
Why me?
It's a chorus.
Okay, does everybody understand this? N to the n Feppel? You sure? Well, we'll find out. Wait. How come nobody took a picture? We got it on video.
Yeah.
Take a picture of the video. Can you snapshot a video?
Yeah.
Does it come out clear?
Oh yeah.
I never tried before.
That's super clear.
All right, today we start chapter 10, which is on series. Now, the series, okay, the definition of a series is the sum of the terms of a sequence. So let's look at a sequence. 1 plus 1/2 plus 1/3, 1, 1/2, 1/3, 1/4. 1, 1/2, 1/4, 1/8. I'm going to try to give you an easy one. This is called a geometric sequence. If I add these terms, what do we call it now? A geometric series. Sequence, series. So when I taught Algebra 2B, I remember I taught it 3 years ago. This is what I had to tell them. A sequence has commas. A series has plus signs. Does that help you?
No.
So today, this whole chapter is series. We're going to be adding the terms of the sequence. But you have to know, you got to get the full, okay, look. How do you write the explicit formula for this sequence? Easy, yeah? A sub n equals, okay, it's geometric, right? So first term times r to the n minus 1.
Yes.
Okay, now, how do you write this series in a more compact notation? Sigma
0 to n.
n equal 1 to infinity. Okay, this is what you're going to get on the next quiz. I'm going to give you this and you fill in the box. 1 times 1/2 to the n minus 1. You just take that thing and put it here. This sigma tells you to add it up. Oh. Remember, sigma is the Greek letter for S, which stands for sum.
Don't forget the dx.
Do you see the
Yeah.
you see the relationship between the two?
Yes.
Okay.
1 has plus.
Now I guess now's a good time, as good a time as any. When you have a geometric series, if the absolute value of r is less than 1, if the absolute value of the common ratio is less than 1, then the sum of an infinite geometric series is what?
First term.
First term over 1 minus r. But you gotta make sure that the common ratio is between -1 and 1. Otherwise, you're gonna end up with something ridiculous like this. 1 plus 2 plus 4 plus 8 plus 16. If if I keep on adding these numbers forever, what are you gonna get? Oh, Mr. Park taught me this formula. First term over 1 minus r, what's the common ratio? 2, so 1 over -1 is -1. If you add up all of these numbers forever, you get -1. Mr. Park taught me that.
Plus C.
No! The common 2 is not between -1 and 1. You cannot use that formula. You can only use the formula when r is between negative. And do you guys remember doing the Coke snowflake last year?
Oh.
You guys did that in Mr. Ye's class? Coke snowflake? You didn't like it. And then on the test, had the Coke anti-snowflake, yeah?
It's over.
Why am I saying that on the video? Yoshida.
It's wrong when you show it, where it's like equal to -112.
Oh yeah, I don't know. You mean this thing?
Yeah.
Yeah, I don't know. That's not right, right? It's not right. Okay, okay, these are the tools. Now this is what you're gonna have to do tonight. Now what the heck is a power series? Now I gotta start all over. This is the remedial math you have to know. What is a power series? A power series is,
It's a series.
wait, that's not even how you spell power.
Power
Power. You know what? See, that's what happens when you get old. You look at things and then they just get jumped up. I don't like it! A power series is a series of the form, I'm going to be careful on this one to get it right. N equals 0 to infinity, a sub n, x to the n. There you go.
Yes.
Okay, let's expand that. What's the first number I should plug in for n? 0. You have to look at this number. Be careful now, because in the book there's some trick problems. Sometimes they start at 0, sometimes they start at 1, sometimes they start at -1. You gotta look. Okay, what happens when I plug in 0? You get a sub 0. What happens when you plug in 1? A sub 1x. What happens when you plug in 2? A sub 2x squared. A sub 3x cubed plus ... forever. This is, it's an infinite polynomial. That's what a power series is. That's because polynomials are the easiest functions to work with. It's easy to take the derivative. It's easy to integrate. That's why power series good. Fire bad. Okay, now remember the 5 power series that we learned last year?
Yes.
Now they're gonna come into play. You gotta memorize those 5 power series. So let's review one of them.
E to
E to the x. Okay, now we're not gonna derive it right now. We're gonna do. I think 1 or 2 sections from now we're gonna derive it. Right now you just memorize them.
1
1
plus x
plus x squared over 2 factorial x cubed over 3 factorial plus .
Box that.
And what is the does anybody remember the interval of notation of interval of convergence for the power series?
What is that?
Negative infinity to infinity. That means you can plug in any number for x and it's going to converge to e to the x. What do you mean interval? Okay, let's do this. 1 plus x squared plus x cubed plus ... That's an infinite geometric series, right? Don't I keep multiplying by x every time? So how do you find the sum of an infinite geometric series? First term over 1 minus the common ratio. But does that work for all real numbers?
No.
No, because what is the common ratio right here? What do I have to keep multiplying by? X. So the absolute value of the common ratio has to be less than 1. And doesn't this mean x is between -1 and 1? We call this the interval of convergence. That means these are the only numbers that you can plug in for x where the series will converge to some number. So you can't just know the series, you also have to know the interval of convergence as well. Okay, these are the things you're going to do in tonight's homework. Write this series using sigma notation. We did all of this stuff last year, so I'm going to give you this in a quiz, like 0 to infinity. Like, fill in the box. So basically, if you think of this as a sequence like this, x squared over 2 factorial, x cubed over 3 factorial, you just put the explicit formula for the sequence in the box. except you gotta start at 0. So what you might wanna do is change this to x to the first over 1 factorial, and what do I change the 1 to?
0.
X to the 0 over 0 factorial, because 0 factorial is 1, right?
X to the n.
So is there a pattern to this? 0, 1, 2, 3.
Yes.
Duh.
Yeah, so x to the
And
n over
N factorial.
n factorial. Of course,
box them.
yeah, no, that's that. But what if they said this? What if you started at 1 instead? How will this formula change?
And minus one.
Minus 1.
X to the n minus 1 all over n minus 1 factorial. Right? So you have to be able to adjust in your direction. Okay, so that's one of the things. Another thing about power series, since it's an infinite polynomial, like I said, it's easy to take the derivative and the antiderivative. So, when you take the derivative, it's easy. You just take the derivative term by term. Okay? So, you have this, they're equal, right? What happens if you take the derivative of both sides of this equation like this? Okay? We already know, what's the derivative of e to the x?
E to the x.
E to the x. Okay, well, let's pretend we didn't know that. This is what we did last year, yeah? How do you take the derivative of this series here? Well, what's the derivative of 1?
0.
What's the derivative of x?
1.
What's the derivative of x squared over 2 factorial?
X.
Put the 2 in the front, the 2's cancel out, and you get x.
X squared over
Put the 3 in the front, the 3's cancel out, and you get x squared over 2 factorial.
E symbol.
Oh! Let's just do one more for funsies. Put the 4 in the front, the 4's cancel out, what's left? X cubed over 3 factorial, and then you go, hey, you
What's
somebody.
C?
What's that?
E to the X.
That's the power series for e to the x. So last year, that's how we learned it, right? The derivative of e to the x is e to the x. We did it by using power series. Okay, I think we gotta do one more. Shall we?
Antiderivative.
No, wait. Let's do this one. Tan inverse x. Okay, who am I calling on? I'm looking at this side of the Tamura. Power series for tan inverse x.
X
Yeah.
minus X cubed over 3 plus X to the 5th over 5.
Okay, good. No, why are you guys doing that? It's like, this is like breathing. Second nature. Okay, now what if we didn't remember the derivative of tan inverse x is 1 over 1 plus x squared? Let's just pretend. Okay, well, we can find it by taking the derivative term by term. So the derivative of tan inverse x will be the derivative of this infinite power series here. What's the derivative of 1? I mean x.
0.
See, I'm thinking ahead.
1.
1. What's the derivative of this? Put the 3 in the front to cancel out.
X squared over 2.
No.
Never mind.
No, it's not 3 factorial, it's 3 now. Plus,
Try.
put the 5 in the front,
X to the 4th.
minus,
X is.
hey,
Use some.
you somebody. That's an
Already.
infinite geometric series. What is the sum of an infinite geometric series? The first term over 1 minus the common ratio, which is? What do I have to keep multiplying by to get the
Negative
next
x.
term? Negative x squared. Hey, that's 1 over 1 plus x squared.
Tan inverse.
That's how we did it last year, but of course now we already know, right?
Memorize.
Okay, you know what? I think we gotta do one more because some of us still look befuddled.
Actually.
No, I think I want to do, pick one, sine or cosine.
Cosine.
Wrong. Okay, let's do cosine.
1.
Right.
Cosine.
Try.
No, Tran already went. Kanashiro, power series for cosine.
1
No?
minus x squared over 2.
Enough of these stalling techniques.
What is the exclamation point thing?
Factorial.
Oh yeah,
Question
factorial.
What's the exclamation?
X4?
Okay, and you guys know from last year, once you know the first two, right, you just follow the pattern, right?
Random number.
Oh, I get it now, Mr. Park, because cosine is an even function. I get it. What's an even function?
And subtract.
Okay, before we take the derivative, you already know
I'm
the
trying to
derivative of
stop.
cosine is negative sine. Write this using sigma notation.
If it points
Okay,
out.
fill in the box. Now, you probably want to write one as x to the 0 over 0 factorial, right? To follow the pattern. Okay, so the first thing you notice, the thing goes positive, negative, positive, negative. So you're going to write negative 1 to the, now remember, if you plug in 1, you want to get positive. So do I write n or n plus 1?
Plus one.
Yeah. Or it can be n plus any odd number, but typically we use 1. Now look at the top numbers, 0, 2, 4, 6. Is there a pattern to that?
2n.
Yeah, that's arithmetic. Common difference 2. So what do I write?
2n.
And then adjust.
Minus 0.
If I plug in 1, I want to get 0.
Minus 2.
Minus 2. All over. And do you notice that the denominator factorial is the same thing as the power? Right there, the x is right there. And then the denominator is the factorial is the same as the power. So 2n minus 2 factorial. Okay, but what if, not what if, it's gonna happen, people. What if we start at 0 instead? How is this thing gonna change? It's gonna be negative 1 to the n. Or you can put n plus 2, but we either use n or n plus 1. That's the standard convention. And then
2n.
2n, and then you adjust. Wait, I forgot the x again. So 2n, and then adjust.
That's it.
Yeah, that's it. So therefore, all over 2n factorial then, right?
Yep.
So yeah, you gotta be good at this.
Box that.
Yeah, oh, I already paused. Okay, now let's take the derivative. Let's pretend we didn't know the derivative of cosine is negative sine. So the derivative of cosine x is, you have to just take the derivative term by term. Let's put the 1 back in. I'll do the first one, 0. Who's got the second one? Ishihara.
Negative x.
Is that right? Oh yeah, it is. Okay, next one here.
X cubed over 3 factorial.
Okay. Next.
Negative sign.
What?
X to the 5th over
X to the 5 over 5 factorial, and then A.
You somebody.
Do the opposite of somebody.
Sign.
Yeah. So that's negative sine x.
Plus C.
No, we're taking derivatives.
Oh, yeah.
There's no plus c with derivatives. Okay, now, so that demonstrates how you can integrate to differentiate term by term, but what about integrate? Integrating is, what kind of game is that? If you were doing regular notes, why would Ishihara be looking at it? You think teachers are stupid? If it's not interesting, Ishihara's not going to look at it. Now, what was I even talking about? Okay, so you can differentiate term by term, but you can also integrate term by term, but you got to do a little trick here. Okay, so let's go. Okay, which one haven't we seen yet?
Sign.
tangent.
What we did called?
Natural log.
No, let's do sine then. No.
We're done.
Okay, let's do natural log then. Natural log 1 plus x. What's the power series for this? Olga.
1
No.
X.
x minus x squared over 2 plus x cubed over 3.
Okay, you guys got that one. Okay, here we go now. Wait. I didn't want to do this one. No, because it's not going to come out to something you recognize. Okay, no, you know what? Let's do it. No. No, we're not gonna. I'm sorry, we're doing another one. Let's do sine x. What's the power series for sine x? X minus x cubed over 3 factorial plus x to the, that's okay, because we went over all 5 power series. Isn't that good? Okay, now, we already know, what's the antiderivative of sine x? We already know. Negative cosine x, now is the time.
Plus C.
Plus c. Okay, but how can we use this to find the antiderivative if we didn't know that. Well, you can integrate both sides, but you gotta be careful now. You gotta do this. This is what you gotta do. You gotta change, well, you don't really have to change the x's to t's, but it works a lot better if you do. Okay, you agree? So what I'm gonna do now is I'm gonna integrate both sides with respect to t from 0 to x. This. Integrate both sides with respect to t from 0 to x. Okay, here we go. And okay, so here we go. Integrate both sides. What's the antiderivative of this thing?
T squared.
What? 1/2 t squared.
1/6.
No, 1/24.
We cannot even do simple.
1/24.
Okay, how about just go
Before.
make the power 1 bigger,
4 factorial.
put the reciprocal in the front.
4 factorial.
No. Oh yeah, 4 factorial, you're right. Okay, then the next one,
T to the 6.
t to the 6
6
Six
factorial.
over 6. Okay, now you got the t to the 8 over 8 factorial plus dot 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 from 0 to x. Okay, plug in the top number.
X.
1/2 x squared.
1/2 x squared minus x to the 4th over 4 factorial plus x to the 6 over 6 factorial minus x to the 8 over 8 factorial plus dot 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 minus, now plug in the bottom number.
0.
0.
Hey, something's not coming out here. Did I do something wrong?
No.
Cosine.
0 plus 0, it's all zeros over there. So this is what's left.
Okay. The first one is.
No, we're missing something. There's gotta be a 1. Where's the 1? There should be a 1.
It's gone.
Right? Because if it's going to be cosine, it's supposed to come out. What's the antiderivative of sine?
C.
Cosine.
Negative cosine. So it's supposed to come out to negative cosine. So the first term should be a negative 1. Where did the 1 go?
There's plus C in the end.
No, but there's no constant because this is a definite integral. There's no plus c. This is a definite integral.
0.
Where did the 1 go?
Like an X-Files
0
game plan.
plus T.
Where did it go?
Mathematics.
It's not.
No, for real. You see we're missing a negative 1 in the front?
It's the greatest mystery.
Where did it go?
Math is wrong.
Well, I think you have to do
It's x to the 0 over 0 factorial.
No.
That is
No,
wrong.
but where did it go for real? This is not a joke.
For real.
It disappeared.
X to the 0 over
Okay, you know what? I don't know where it went. I lost it.
Must be
It's
unsolved.
lost.
Wait, Mr. McCarthy,
Yeah.
that's cosine, right?
If
So
there
then
was
it's-
no, but you need the negative 1. If there was a negative 1 plus this, then that would be negative.
That series is cosine, so when you plug it back in 0, like for instance, okay, say, so you have like a series, and then when you plug in 0, it has a value, or when you plug in 0, it's 0, but when you plug the value into the trig function, it comes out like value. So like for that one, it should be,
Yes.
that should be 1.
You're right.
What?
Class is over?
Okay, I will try to find that negative 1. I thought we were gonna finish early today.
We did. We finished at 2:10.
That's right. Oh my goodness. Oh my goodness.
Oh my gosh.